mientras la profesora Elena llega, entonces les recuerdo que hoy tenemos las primeras dos sesiones del curso y mañana al principio de las clases vamos a tener el test de estas dos primeras sesiones, tanto del curso de la mañana como de la tarde. Okay? Tomorrow at the first 15 minutes or 20 minutes we will have the test of the sessions of this morning and this afternoon. It's very important to present the test even if you think you are not able to pass it. Okay? It's just to check that you are following the lectures and you are following the material. Presentan el examen aunque no, digamos, aunque crean de pronto que es difícil para ustedes. El material es principalmente son exámenes tipo test, o sea, selección múltiple, un problema pequeño, de tal manera que no piensen en un parcial porque no hacen normalmente aquí, que son parciales de 6 horas, ¿cierto? Haciendo problemas de pulgada. Okay? The tests are simple, but not easy, of course. But in any way, are not tests or are not exams of 2 hours long. No sé si tienen alguna pregunta hasta ahora. Estamos comenzando, estamos viendo cómo nos ha ido. Ven bien el tablero. Alguien puede decirnos de pronto si la letra está muy pequeña para que vayamos ajustando esos detalles. Hasta ahora todo está bien. ¿Todos escribieron? Ok. Les recuerdo que estamos transmitiendo vía live stream y estamos grabando y el video se monta a YouTube por si ustedes quieren repetir o volver a ver el video más tarde. Bueno, para ver el video en vivo, les recomendamos abrir una cuenta en Livestream y suscribirse o hacerse seguidores de astronomía. Inmediatamente se acaba la clase, queda el video en el Livestream grabado. ¿Okay? So you need to be a follower of Astronomía UDA. Astronomía UDA in Livestream, and you will be warned, you will receive an email or something, signal telling you that the video is available online. And for the YouTube videos, again, we have a channel, which is the channel of Astronomía. Okay? Please ask everything, anything that is in your head. Please ask. You have to use the fact that you will have Elena and Bernard here. Aunque the output is okay, if you put, I put basically here. The photocopies of the notes are just coming, so I will interrupt a minute just to give you the material. Okay? No, because it's better to follow using the photocopies.
not a 90-degree with respect to our detector. So, for instance, let's have a source, area dA. Okay, this is the perpendicular to the surface, and let's assume that we have a source here at an angle theta. Okay. So my source is now here. So I ask, what is now the energy that crosses this area in a time dt in this direction? So I want to know the energy that crosses this area in a time dt in this direction. Any idea? Yeah.
The intensity per dt, the differential of area.
dA. Not dA.
dA cos theta.
dA cos theta.
The omega.
The omega. Very good. So what did you say dA cos theta?
Because is the projection of
The
the
projected area. That's right. So the energy that is crossing this area is actually seen the projected, only the projected area in the perpendicular direction. In fact, if my source was at 90 degrees, there will be no energy crossing my surface. And this is what it's saying. Okay? Because it doesn't see any surface at all. Okay? The energy that crosses an area A in a time dt using the flux. Please tell me. Now I want the energy that crosses my my area dA in a time dt using the quantity flux. Who's talking? That's easy, that's easy. Easy.
What's the dA?
A because this is the energy that crosses overall the area dA in a time t. Okay, from any direction. Okay, so now I equate the two, and I find the relationship between F and intensity. This is actually intensity in the theta direction, right? So let's call it dF. dF is equal intensity cos theta, which reminds me that the unit area is projected times the omega. Okay. So that is super important. So we're going to do 3 exercises on this. So the way I remember it more or less is that these two quantities, okay, has to do with, if you want, with the receiver. This is my receiver, and this is theta, and the intensity with respect to my receiver. The omega has something to do with the size of the source. Okay, so let's take the simplest source possible, which is a sphere. So let's start with a sphere, which which is emitting isotropically. So the intensity is the same in all directions. So isotropy equal E does not depend on direction. Okay? And let's assume that this time is not transparent but is opaque. We are going to rigorously define what is transparent and what is opaque. In words, opaque means that we can see the light only coming from the surface, or a small layer in the surface, very related. Okay? Now I put myself at the distance, so this source has a radius r, big r, and we are at the distance little r, and I put my detector like this, perpendicularly. Okay? Here. Okay. So I want to calculate the flux that I measure from this source. Okay. So where do I start? Where do I start? From the definition, right? Let's start from the definition. Okay. So let's take an angle, an intensity is coming to me from an angle theta. So here, this point is emitting isotropically, right? So there is a ray of light which is coming towards me at an angle theta. And this is the intensity in the theta direction. But this is isotropic, I can just block this and say just intensity. Okay. So I know that the flux that is coming from this direction is E cos theta. Yeah, but from which solid angle I'm going to collect an intensity at this angle? From which solid angle? This you need a little to visualize. It's isotropic, so my solid angle is everywhere. This is an angle theta from me, right? So this is the edge on, edge. Let's say face on, face on. This is the center. Now I'm facing, we are facing the source. And so an intensity I is coming from between a distance, let's say r plus dr, right? Okay, and basically, okay, which you know is basically linked by, okay. Let's say that r prime is any distance between 0 and big R, okay? So the intensity comes from r prime, such that so basically you have r sine theta. Okay. So the projection of r onto the sphere. That's easy. Okay. So how do I calculate the solid angle? Okay. So it's my fault because I didn't formally define the solid angle. Okay, so let's formally define the solid angle. So solid angle. Solid angle. Okay, so in general, okay, not just area.
The another angle. So waste another angle, the V and the theta.
Oh, okay. So let's okay. This is the projected area. That's what I'm telling you. Right? It's the area perpendicular to R. Okay. So let's write it like this. This is the perpendicular direction, and this is the cursor of the R direction. Okay. So it's the projected area perpendicular to the distance divided by the distance squared. Okay. And in spherical coordinates,
Square sin theta. Square. Yeah. R square.
okay, R squared, and then I divide by R squared,
Sin theta.
sin theta,
D theta.
d theta, d phi. Yes. And so this cancels out. Very good. So, okay. But here I have, so this is my angle theta, and this is my angle phi. Okay. So the solid angle has phi symmetry, so I can write 2 pi sin theta in d theta. Okay. Now, just as an exercise, because we will use it a lot. What is the total solid angle? If I integrate this from 0 to 90 degrees, what did I get? So it's okay. It's 2 pi because it's 2 pi stays 2 pi, and then I integrate this, which is minus cos theta, right? From 0 to 90 degrees, so I get 1 minus cos theta. Now, in general, we are very far from, so our distance is much larger than the size of the object, right? So I can tailor expand cos theta, right? And this is a even right function. So it's the first order is 1 plus theta squared half. So what I get is pi theta squared. This is for R much larger than the size of the source. And this is the solid angle under which I see a source which is far away from me. Okay. But let's go back to our exercise. So now I know the solid angle. So I can substitute that in here. So I have 2 pi sin theta and d theta. Now to get the total flux, I just need to integrate this over all possible direction from which I receive the light. Okay. So there will be a maximum theta. We call it I don't know, theta C or F or from which I can receive light, right? Okay. And what is this? I have all the variables to estimate this angle.
19.
I have the distance, I have the size of the source. So right? Okay. So basically, it's when this R prime is equal R. Then I don't see anything anymore, right? So the relation is R equal little r sine theta c, right? Because I slice a small solid angle, then another one, then another one. When I'm arriving at R, I don't see any light anymore coming from it. Right? So this is the relationship. Okay. So f is the integral from 0 to theta c of this expression here. So it's okay, it's up to constant. So sine theta cos theta d theta. There is a usual trick that this one is minus cos theta. So in the end, I get. Okay, it's a little bit difficult to calculate by heart. We can do. I can just jump here. Sine square theta c. Okay. But this one is big R over little r. So it's pi I. So it's r over little r squared. Okay. This is my flux. The total flux that I received from an homogeneous sphere at the distance little r. Okay, so we have two things. So again, we have this inverse square law, right? The more distance you are, the smaller is the flux, and it goes as r to the minus 2. Okay. Then, for little r equal r, so the flux from the surface is pi e I. This is very important because we reduce it many times. So when the source is isotropic, the flux and the intensity at the surface are just related by pi. That's it. Okay. And that's interesting. Okay. Another maybe interesting thing is the following. I will write it here. Okay, cancel something. So the flux is just let's do this. It's pi I sin square theta c. Okay, but we are very far. Again, it's pi I theta c square. And what is this? We derived it before. I just cancelled. This is the solid angle under which I see the source. You remember that the solid angle was basically 2 pi 1 minus cos theta. So it's very easy. The flux I receive is just the intensity produced by the source times the solid angle under which I see the source, if it's very far. Okay, now let's complicate things because that was a very easy example. Okay? Now, so the Swift satellite is a satellite that observes or launched primarily to observe gamma ray bursts. These bursts of gamma rays that goes up in the sky 3 times per day. Okay? And we think associated with massive star exploding. So let's have this is the second exercise. We have out my detector. It was observing a gamma ray burst. So it was pointing towards a gamma ray burst in X-rays. So observing. But accidentally, a supernova, so which is another manifestation of the explosion of a massive star, exploded here at an angle theta. At a distance r. Let's call it alpha. And you will get alpha. Okay. So what is the difference? Maybe I'll just wait a minute so that you get the
Sorry, it's just a minute.
yeah, that's fine.
Everybody has one? If not, if somebody doesn't have one, it's PDF, the web page. I think it's enough, but anyone? Okay. Yes. This is for tomorrow, for the tomorrow test. Yes. Oh, no.
Okay, so I go back to my, okay, so the first exercise is we derive the flux and its relation with intensity and the solid angle of the source. Okay? Second exercise, now I have the receiver in this direction and my source is an angle alpha. So what is the difference between this configuration and the one before? What is the difference? It's not perpendicular. Before, my detector was looking, staring at my source, okay? But this time, the detector was looking at something else. So it's the supernova exploded at an angle alpha. So it's R, the distance to the source, is much larger than the size of the source. You can show by yourself that the flux is like this one, so it's I times the solid angle under which I see my source. Okay, the solid angle under which I collect my photons, but times cosine alpha. And you can show it mathematically with this condition. Okay. Okay. The third case, it's a little bit more complicated. So let's say that I'm a distracted observer and just looking at the sky, blah, blah, but then someone asked me, okay, but takes the flux of a galaxy or an AGN with an accretion disk, which is at an angle alpha from. So a galaxy, like a spiral galaxy, that has a disk. Okay, so it's not spherical anymore. We now have a disk. And chances are that disk is randomly oriented with respect to us, right? Y should be perpendicular. In fact, our, let's say that our, our disk is at an angle beta. This is my galaxy. Or accretion disk, like an AGN has an accretion disk, and I want to calculate the flux from the disk only. Okay. So now it's slightly more complicated because I have an angle that has to do with my detector, which goes here. This is the angle that has to do with the detector. And the angle at which my source is goes in the solid angle, right? Because let's imagine that I'm very unlucky and my galaxy is at this angle. I don't see basically anything, okay? So the solid angle will be 0. But this angle will be still cos alpha. Okay, so you can show that the flux from a disk configuration is basically, okay, it's I cos alpha, no? And then times the solid angle under which I see the source, okay, which is the area of the disk, the proper area, this one, but projected. So it's cos beta divided by the distance squared. Okay. This is a disk, so it's I cos alpha pi r squared divided by d squared cos beta. And so again is this is the theta square, the angular size of my source, right? We did it before. So again I have I cos alpha. Okay, we can say theta square cos theta of the source.
Sorry, Elena. This d square is the same as...
Sorry. You're right. That's very bad. You're changing notation. Sorry. And this is R, the size of the disk, the radius of the disk. Sorry. Yeah. This is always the distance and okay. Something like that. Okay, that's it for the relation between intensity and flux.
I have a question, because since the disk is oriented in an angle beta, the angular size is not anymore d over r over little r, right?
There is cos beta.
But r divided by little r, okay, is not anymore the angular size.
Yes, so it's okay.
Right? It's just a question.
So it's okay. It depends on how you define it. Okay. So, but so we're defining before theta as r divided by little r squared. So that's why I use it here.
Okay.
But the important thing is that it's the projected area divided by little r squared.
Okay.
Yeah. Otherwise, you can absorb this cos beta inside and have the projected r squared. Times cos beta divided by r squared. Okay. Okay. Yeah. So this part ends here. one, and so definitions and also the relation of other quantities with the intensity. Okay. And now we are going to see something very important. So how the intensity changes when it's propagating through the medium. So how the intensity changes as it propagates through the medium is regulated by what is called the radiative transfer equation. We are going to build it and use it.
In section 1.8, yes.
Yes, yeah. Okay. So we have our intensity. And so far, we have always worked in the vacuum, right? And in the vacuum, the intensity remain the same. Okay, so we can write that the change, the fractional change of intensity as the ray crosses a distance ds. This is in vacuum.
Sorry for that. This S, ds is just a space?
Yes, it's just yes. So so basically I'm emitting some photon here.
Yeah.
And I have a certain intensity, so energy per unit second that crosses the unit area perpendicularly. Then I'm going to measure my intensity after a length ds, and I make the difference, and I see that is zero. So the intensity here are the same. So this is a path, the length in centimeters. Okay. Then let's say that now I have some metal between the point of emission and the point in which I measure intensity. Okay. So first of all, let's assume that this metal just emits. So what happens is that I have my light, I launch my ray, and if you want, you can see visually what I see is that other photons join up the ray, so that the ray or the number of photons increases as the ray propagates. So how do I write it mathematically? That the difference between intensity here and here is just emissivity. Let's do it as emissivity. You remember what the emissivity was? Emissivity is very important property of the source. It is the energy per unit volume per unit second, so it's the power density per unit sterility. Okay, so let's again visualize it. I have a piece of the source. My intensity comes in, and here I have my intensity plus what has been collected here. Right? So this DAI is what has been collected along the path. All these photons that were emitted are joining up. And so here I see an increased intensity. This is with emission only. if I have now not a small dn, this is ds. Okay. And now let's suppose that I have I take a source with radius r, which emits only. So what is the relation between I and j? If j is constant. So I'm having my source, j mu is the emissivity, and is equal at all points within the source, and the ray is traveling a distance r. So I just need to integrate it, right? So I just need to integrate from 0 to r, j mu in ds, and this is equal my intensity, initial intensity. I wanted to write it here. Okay, so here minus my initial intensity. Right. I integrated dr. This one. Okay. So if this is constant, what do I have? So I is equal
J out zero.
the initial intensity plus j nu times r. Okay. And if I don't have any illuminating material, so initial intensity is 0, we recover with this is 0. We recover that intensity is j nu times r. Remember, for a transparent source. So we have formally recovered what I just said before. This is for j mu constant. Okay. Okay, so now let's take the opposite. Yeah.
If the initial intensity is 0, where are we supposed?
No, I mean the initial intensity is the intensity here. For instance, let's take it as a molecular cloud. This is a molecular cloud. Let's assume that you have a star here that is illuminating the molecular cloud. So at this point, if I measure the intensity, it's not 0, because this intensity coming from maybe a giant star. Okay? So it's I0, but then if I measure the intensity here, I have also to collect the photons produced in the molecular cloud. Okay? If now I don't have stars, the intensity here outside the cloud is 0. Okay? That's it. Okay, so let's take the other case in which my source is not emitting. Let's say that it's not emitting, but it's absorbing. It's taking out photons from the ray of light that goes through. Okay. So the fractional change of my intensity is proportional to what? Let's think. Let's take our source again. Okay. Let's have an initial intensity here. Okay. And I have a medium that absorbs only, take away photons from this direction.
Proportional to the density of particles.
Okay, so something related to the density, very good. So there will be something related to the density, which actually is called this is called emissivity or emission coefficient, and this very good. It should be proportional. I put a minus because it's heating. Right? Alpha, which is called the absorption coefficient. Absorption coefficient. Okay. And alpha is indeed proportional to the density of the atoms, but also to their cross-section. Are you familiar with cross-section, like in quantum mechanics, the cross-section? And in general is specific. So the cross-section for a specific frequency. Okay. But not only. So, for instance, I start from here. The intensity at this point, or the intensity at this point, which one is lower?
The first one.
The first or the second?
The second.
The second. So the fractional change of intensity is also proportional to how much the length, how much you travel, right? Yes.
I have a question.
Yeah.
What if, in this case, the media absorbs the light? So it must to be another contribution in the because this particle begins to emit like a black hole, black body. So the intensity must to increase in the infrared.
Okay. So what he's saying is that it's a little bit unphysical to think about a source that absorbs only or a source that emits only. It's very difficult. Okay. So we take these two cases separated, and then I show you that the general is the sum of the two, in which consistently you take into account emissivity and absorption, and then particular frequency. Okay. Okay, so this is emission only, this is absorption only. Let's go to solve this equation. So I just erase a little bit things around the. So this is emission only. So it's clear. This is emission only, and our solution was I equal initial intensity plus J naught minus R when this is constant. In general, you need to integrate, okay, if this is not constant along the range. Okay. Okay, now I want to solve this. Any idea? What does it look like? An exponential decrease. The more you travel, the more you exponentially deplete the ray of light. In fact, the solution is quite simple, is I equal the initial intensity times E to the minus the integral between 0 and S of alpha mod ds. Okay. Now, this is intuitive, right? The more you travel, the more you exponentially deplete. It's also for any kind of decay, right? Okay. Now I say one thing, and then we go back to this quantity that maybe you know already. Okay, so, but as we were saying before, the general equation has to take into account that intensity is absorbed, but also gets contribution from emission. Okay? So, the general equation is that the fractional change of intensity when the path travels a distance ds is increased by the emissivity of the source and depleted by the ability of the medium to absorb. Okay, this is our tool. Okay, but before solving it, this is the last thing we will do today. I want to come back to this quantity because this is very important in astrophysics. The optical length. Okay. So I'm not being very. I'm being a little bit loose in going from a classical description of light in terms of ray and a quantum physics description in terms of photons. So I keep doing this because I feel that maybe describing two different ways is clearer. So I will do it again here. And also there are some processes that are for me are best described in terms of photons, like interaction between photons and particles, and others that only in terms of rays. Okay. So let's define d tau equal to alpha ds. What I'm actually saying here, I'm saying that a source, if I travel in the source a path ds, or in the medium a path ds, it doesn't tell me anything about what it does to my ray. Okay. For instance, if there is no absorption, okay, I know that the ray is constant. And so with this quantity which is tau, is the optical depth, will be 0. So if the optical depth along the path is 0, I know that there won't be any absorption. Even if this is megaparsec, even if like 100 megaparsec, doesn't matter. If there is no absorption, my optical depth is 0. So you see, it's very intuitive to think in terms of optical depth and not in terms of actual length traveled. Okay? For instance, let's see. So I can rewrite the equation for only absorption in this way. Minus tau. Right? Okay. So let's start with my ray. When I travel a physical length so that tau is 2/3, I get that I divided by I0 is 0.5. So there is something special about 2/3, and often astronomers use 1, which is that when you travel an optical depth of nearly 1, your intensity decreases by half. Okay, so let's now think in terms of photons. I start with 100 photons. After a tau equal 1, only half survives in this direction. The other get absorbed or scattered away from this direction. So we can think in terms of probability. Traveling a tau equal 1, a photon has 50% chance to survive. Okay. So this is a spatial place. So we call a source that have tau much greater than 1 or 2/3. So this is its 1/e². It's called optically thick that is tau much less than 1 is called optically thin. So what does it mean? That in this source, the photon has less than 50% chance to be created within the source and to escape it. In this source, they have more than 50% chance to be created within the source and leave it. Okay. So before I was saying transparent for this source and okay for a source with tau much greater than 1. But this is the formal definition. Okay. So how much time do I have? So the only thing I will do now is to solve this equation formally and then in a specific case for an optically thin and optically thick source. We will discuss it and then for now, for today it's okay. Okay. Okay, so if I use this definition, right, I can rewrite my general equation of the radiative transfer. So this is radiative transfer equation. So I divide by alpha nu, and I can write the incremental change of the intensity after the ray has traveled a path d tau, okay, is what is called the source function minus the intensity, where the source function is the emission coefficient divided by the absorption coefficient. Okay. So this one has the unit of an intensity. Earth is a power per unit surface per steradian. Okay. And as a physical meaning, we will see one or two in the next class example for this. But what is intuitive is something to do with the source, the property of the source, right? Is its emissivity, the ability to emit, divided by its absorbability. Okay. So it's very simple. The way the intensity changes depends on the property of the source and is proportional to the intensity, the absorption. Okay. So it has a formal solution, which you find its equation. Okay, I'll go back. So the formal solution in the general case is I of tau equal the initial intensity times t minus tau plus integral of 0 to tau nu on t to the minus tau nu minus tau prime, the source function tau prime into tau prime, where tau prime is the variable of integration. Okay, and tau is the final location in the source. Okay, so this is very ugly, but already we can see something, right? So the intensity, so this is my source, is always spherical, isn't it? Not all sources are spherical, just because. Okay, so this is, I have an initial intensity, and and I'm measuring it I here after a struggle, an optical depth counting. Okay. So we can already see something here. So the intensity that I measure here with my detector is the initial intensity decreased by the fact that it has traveled this way. So this is what is left from my initial intensity. Like, remember at the start that irradiates my cloud, for instance. Okay? And this one instead has something to do with what happened to the ray along the path. Now we're going to solve it for a very simple case in which the source function is constant along the path. So the emissivity and the emission coefficient and the absorption coefficient are constant. I have a homogeneous source, you see. Okay? And then when you do this, it's easier to see what the solution means. Okay? Okay, so I'm going to solve this. I mean, I'm just giving you the solution, but it's very easy to derive when the source function is constant. Then the intensity that I measure here is the initial intensity decreased by the path, the optical path that is traveled, plus the source function 1 minus e minus tau. Okay, so who wants to tell me in words what this means? What does this term mean? So the intensity I measure, I've already said, is the initial intensity decreased by the fact that it's traveled the path, plus something else, something that has happened in the source. Who wants to tell me by words what it means? Yeah?
If those,
Yeah?
the source function is the ratio of emission to absorption, right?
Yeah.
So that's like the overall light that has been emitted in that distance.
Yes, but I
By
don't
the-
take this one. I take.
So I said,
No, that's right. It's this, but not only this, because I have this term.
yeah.
What does it mean?
Minus E says that it's a very
Growing.
it's growing, not decreasing, but growing. The minus E. The minus
You mean this one is growing?
it's there are some columns to the right.
Okay. So let's say, is that clear if I say that, so 1 minus, this is absorption, right?
Yes.
So 1 minus the absorption is what is left, what is not been absorbed. Is the leftover from the emission. This is absorption. 1 minus the absorption is what has not been absorbed. So the emission, this is what has not been absorbed in the travel. So, you know?
Sorry, in the bubble or in the source?
In the source.
Okay.
So because at each point, if you want, it's not really strictly correct, but you can see. In each point, I emit this intensity. But as it propagates, one part gets absorbed. What I measure here is what has not been absorbed. So it's 1 minus what is absorbed. Is that clear? Okay. So that's what it means in words. If I don't have initial intensity, I only have this term. For instance, if tau, let's say, okay, so now we rewrite it. Let's do this. So maybe it's clear. Let's take this equals 0. I'm giving you some examples so you can understand what it means. It's not just mathematics. Okay. So this is if you want emission coefficient divided by the absorption coefficient times 1 minus e minus tau. Okay. Now let's take a source with physical length r. So this is its r in centimeter and tau in optical depth. Okay. So I multiply and divide by r. Do you recognize it?
Yes.
What is it? This is an homogeneous source. So tau along this path is the integral from 0 to r of the emission coefficient in ds. If this is constant, this is alpha times r. So this is tau. So we have j times r 1 minus tau divided by tau. Okay, so now we take two limits, optically thin and optically thick source. So we understand what happens inside. Okay. So let's first take the optically thick one, tau much greater than 1. Okay, so now we are going to understand something that I said at the beginning. There was just a statement, and now we are proving it. Okay, tau much greater than 1. So this is if 1 goes to 0, right? So that my intensity is J R divided by tau. So what does it mean? What does it mean? Can you say it in words? So what I'm doing is to measure the intensity here after it has, this is 0 at the beginning, after it has traveled a very optically thick layer. And I'm looking from this direction. It's a curve. So what does it say? That intensity is the emissivity times r divided by tau. So not the whole r, but r divided by tau. Someone knows how to say it in words? J is the emissivity of the source. No idea?
Just
The energy is in proportion inverse to the density of the main other part.
No. It doesn't mean that in this case. So J is the energy generated per unit volume. What I'm saying here is that the intensity I measure comes only from a very thin layer in which Ji is here. And this thin layer has a thickness of R over tau. So I from here. I see photons only emitted from here. Why I see that? Why I say that? You remember that we were going to derive it. In the optically thin case, I was equal to J times R. Why? Because I could see the whole path. If it's optically thick, I see only R over tau. This part is very important. It's called atmosphere. Atmosphere of an object. If an object is optically thick, we are going to see emission coming just from the atmosphere. That's why we don't see the light from the sun, interior of the sun, but only from the surface, because the sun is extremely optically thick. And we will do an exercise on that. Okay? Okay, so I want to say something else that is important, that we will use it. We'll do next time an exercise on lines, emission lines. We'll use a protostar to do this. So, when it's optically thick, let's come back to this equation. What you have then, look at here, this is the non-zero. The intensity for tau that becomes very, very large tends to what? This one, the link of this one to a very large optical thickness.
This is one.
Okay.
This is function. Right. So when this is very important, when not intuitive if you think of it, when a source is extremely optically thick, actually it doesn't care what happens around it. I mean, unit volume, and what I see is that the photons before me get absorbed. The photon above me also, they don't arrive to me. What it's saying is that in a very optically thick source, the intensity knows only about the local source function. Okay? It doesn't know about what happens around when it's very, very optically thick. So it's a local, it is defined locally, we say, defined locally. While it's optically thin, the intensity knows about the history, the structure of the whole source. Okay, and then with tau much less than 1, and this is the last thing I said, we find what I already said before, intensity is just J times R. I see the whole source. And I think we stop here for today. And if you have questions, then
Okay, that's all.
question on this part?
Yeah, I
Yes.
have a little of confusion.
Yes.
When you ask us about to say these words,
Yes.
not the
Yes. Yes.
Okay. The left part of the equation is due to the travel of light from the interstellar space or something, yeah. And the second one is due to the source itself. Yeah. So we have.
Well, in my example here, yes. So the first part was the initial intensity times the absorption in the source.
Okay.
In the source. Yeah. In this example, what the absorption was in the source. Yes.
But in general.
Yes.
So this equation is related only to the source.
No. So I have a source, but this it just be interstellar medium. So if you have an interstellar medium, so there is an intensity coming from a star.
Don't worry.
It's fine.
Yeah.
I didn't bring my helmet. I hope it's not necessary. Okay, so sorry. light travels with me, the interstellar medium, which is made of clouds and other things, can absorb and emit. So it's also how the intensity from the sun propagates and all these nice features that we saw in the spectrum.
Okay.
So that equation computes also the atmosphere of the Earth.
For instance, if I want to know, this is general for anything. You give me a medium with absorption and emission, and I know how intensity changes. So let's say that this is its intensity from the sun in a particular frequency, and this absorption emission will be those of the atmosphere at this particular frequency. And so I know what is the intensity absorbed on Earth at that frequency.
So if you have source with atmosphere, then the light travel from space, and then the light goes down from the Earth atmosphere.
Yes.
You need to calculate 3 times
Yes,
the
so
same.
So this absorption coefficient will be the sum of the various
Of
things.
the atmosphere of the source, the
Yes.
medium,
Yes.
and the Earth
Yes,
atmosphere.
exactly.
Okay. Oh,
Yes,
that's
and the
true.
emission will be of the emission. But here I used a constant source function.
Okay.
So I was just imaging one only medium.
Yeah.
But you can sum them up.
Do you have a source function for each medium?
Exactly.
Oh.
Yes. And then you sum this, and this is plus, 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 plus.
Okay.
Yeah. Yeah.
Perhaps it would be nice to mention that for stars, the only place where you can observe the intensity is the sun. For stars, we only observe the frost.
Yes, so yeah, that's right. For this reason, that the intensity is just like perpendicular, remember? So we have to be very close to see the just intensity. Usually what we see is integrated flux. We are very close.
There are distinction between intensity and flux.
I think regarding what Pablo just mentioned, the fact that you usually have to solve these equations through different media, and not only different media, but also media where you have mixed stuff, where you have different properties, is very important. And I think regarding to what you just said, it's important to mention that while you can write down the solution of the radiative transfer equation, it usually gets more complicated than just integrating the equation. So I guess you will be telling us a little bit about the fact that there is also numerical solutions for this thing, and I think it's a very important thing these days that people solve.
No, I was not going to say, but so this is the general one, okay? So this is the general one, and it's very important to be able to solve it from a first understanding. So this is my job. But then you can go back to this one and ask yourself what this tau comes from, which are the contribution from me, from the Earth to the source. Okay? So tau is an integral again in a particular frequency of the emission coefficient. If you have different emission coefficient, you have to sum them up, plus, plus, plus. Okay? And usually, what we say is that in real astronomy, so things can be extremely complicated because absorption in one frequency can come from different medium with different temperature density, and so they have different absorption and emission coefficient. Okay, so generally this has no analytic solution, and so people use like computers to integrate them. But this is, if you want to add something about it,
It's very good to have the equation written down, and also know that in most realistic cases you actually need to do some computing in order to solve it, right? Because it can get very complicated. But it's good to have the equation written down. You know that you can in principle solve it. So for any situation,
How can we know if the distance between the emission and the pulse? How can we know what type of element between the dust and the gas? How can we do that?
that's very interesting. So again, what we are using is things that you are learning here in the transfer. So, you observe a patch of the sky, and from its emission and some of the emission mechanisms that we will study here, we can get the density, the temperature, and the composition of that particular medium. For instance, if they have elements emitting a particular frequency, we know that it's enriched of certain oxygen or carbon elements, and we can calculate through lines the abundance. From the continuum, and on lines you can also have density and temperature, for instance, or for continuum emission you can have density and temperature. So basically you always use light to determine the various physical ingredients, then you use physics to calculate alpha and J. And I unfortunately don't have time to tell you how to do this, but alpha and J, from a microscopic point of view, there is a very solid theory, and this was developed by Einstein. And one uses what is called Einstein coefficient to relate the macroscopic interaction between photons and molecule to this macroscopic quantity that I just call it absorption coefficient. Okay? So you need to light to diagnose your medium, but then physics to calculate this through the Einstein coefficient.
If we have I don't know, a megaparsec between the emission and the pulse, how can we know what are the interstellar medium?
Again, you need to use this equation over and over again.
You have to make assumptions about why you think the interstellar medium is composed. That's why it's so problematic these days to solve for a particular type of dust, for example, because you don't really know what dust type you're looking at. You can guess something about what's the dust that you're observing by looking at the spectrum, for example. But there is always the issue that you have to make assumptions about the particular dust type. So you cannot really know what's in between us. But by looking at different sources and solving this equation for different types of sources, you can get a knowledge of what's in between. And then you can predict, and if it agrees with what you observe, then you can say that your assumption was right. But you have a point, it's difficult to really know what you have to do.
Disentangle like the source and the interstellar medium. So as you said, you use different diagnostic. So for instance, you use different lines. Or you use different sources going through the same interstellar medium, and so on. And you try to collect more data as possible to characterize the medium between you and the source that you are studying.
It's hard to be an astronomer. It's not easy.
More questions?
I think it's because it's the first time, so they will be more friendly in the next days, I hope. Okay?
Thank you.
Before everyone moves, I wanted to say una cosita. Muchas gracias a Elena por esta introducción. Yo he visto muchos astrónomos, yo incluido, que ya han pasado cierta experiencia y todavía están confundidos con lo que estas definiciones significan. ¿Qué es el flujo? ¿Qué es la intensidad? Etcétera, etcétera. Es extremadamente importante que haya una sesión así muy interactiva. Por la sencilla razón de que si ustedes van a ser observadores o teóricos, ustedes van a encontrar siempre un universo lleno de cosas, lleno de gas, lleno de polvo, y mucha de la astronomía moderna se basa en resolver estas ecuaciones. Entonces, les recomiendo que miren con mucho cuidado estas definiciones que ella nos dio hoy, porque si van a dedicarse a la astrofísica en el futuro desde el punto de vista observacional o teórico, van a seguir encontrándose con esto. En la sesión de la tarde, Bernard va a empezar su curso de técnicas de observación, y así como Elena nos explicó cómo se produce, cómo se empezó a explicar cómo se produce y se propaga la radiación, el curso Bernard va a ser también acerca de la práctica, cómo la detectamos y cómo los detectores funcionan para detectar. Entonces están muy bien relacionada a las dos cosas. Y luego vendrán todas las aplicaciones de núcleos activos de galaxias, protoestrellas y demás procesos de y no les he tenido que preguntar, incluso si a veces no lo pueden preguntar en inglés, pregúntenlo en español y entre todos
traducirlo.
¿Ok?
Esa es una buena idea. Pregunta en español y aquí Juan Rafael tratará de hacer la traducción.
Antes de que se nos vayan, algunos anuncios sencillos. Les recuerdo que la clase de esta tarde, el curso, comienza a las 2:30. De nuevo, puntuales, para que podamos aprovechar el tiempo. También, todos los días, entre las 9 y las 10 de la mañana, antes de la clase de Elena, los profesores de astronomía, Elena misma, Bernard, estarán disponibles en caso de que quieran revisar algo del material y quieran ver una explicación adicional. Entonces tampoco se nieguen esa posibilidad. So from 9 to 10 every day, probably from 3 o'clock to 4 o'clock, Elena, Bernard, me, and all the astronomy professors will be available at our offices in order to explain anything you want to discuss. Also, you have to remember that tomorrow, before starting the next session of Elena, we'll have a test. So it's very important that from today to tomorrow, you do some rehearsal of the material, read, look at Wikipedia, and all this kind of stuff to pass the test tomorrow. Okay? Mañana tenemos el examen, los tenemos que ir a la casa.